In the last module, we learned what externalities were. In this module, we are going to focus on how the government deals with externalities. And even though we said that through the Coase theorem in the previous module that the market could solve the problem of externalities in the least cost possible, we have found as economists that there are ways in which the government can be involved in making public policy to reduce or eliminate externalities through ways which approach the market system. And that's what we will address in this module. So I'll begin by addressing externality problems with specific public policies. Then I will explain why some government policies to deal with externalities, such as emissions taxes, tradable permits, or Pigouvian subsidies, are efficient, although others, like setting environmental standards, are actually inefficient. Now, environmental standards exist in the United States today. When the government passes environmental standards, whether it's at the federal, state, or local level, these are rules that are made by the government that protect the environment by specifying actions by producers and consumers. In other words, they limit what consumers or producers can do to the environment, or limit the amount of pollution that we can put into the environment. Maybe limiting congestion on traffic highways or things like that. But generally, economists regard these standards as inefficient because they are inflexible. The rules apply the same to everyone. And some producers who may have a greater cost at reducing their pollution may not be able to reduce it at the same cost as someone who has a lesser cost. And so they might be both producing or reducing pollution by the same amount, two different producers, but if one has a higher cost, we would rather the one with the lower cost reduce pollution more, because that would be a lesser cost to society. So environmental standards are regarded as inefficient. Major pieces of environmental legislation in the United States, going back to the Clean Air Act of 1970, have only been around since that time period in the early 1970s. Recent laws, however, have incorporated more market-based incentives to reduce pollution and gain economic efficiency. Now, when we talk about environmental standards, early legislation in this direction was written with a heavy dose of "thou shalt not pollute more than X amount of gunk in the air, water, and or soil." So in other words, the government would pass a law telling producers this is the limit on the amount of a certain type of pollutant that you're allowed to put into the water, into the air, or into the land. But it applied the same to everyone. Regardless of their cost of reducing that pollution, everyone had to reduce it by the same amount and abide by the same rule. So now this was a vast improvement on the unregulated and heavily polluted situations that led to the environmental movement in the 1960s and the 1970s. Because prior to that time, there were very few environmental standards or very few rules in place, and producers could pollute as much as they wanted to. And fish were dying, air was heavily polluted, there was smog in the atmosphere, the country was becoming very dirty. And it was the environmental movement of the 1960s and the 1970s that led to these environmental standards and rules being put in place. But they were seen by economists as an inefficient way to tackle the problems of pollution. These environmental standards are also known as command and control measures for reducing pollution, because the government is commanding producers to reduce pollution by a specific amount and controlling who does it and how much they reduce it by. For example, many cities require automobiles to pass emissions inspections before the license plate can be renewed. We do that here in Colorado. Sewage has to be treated before it can be released back into the environment. These are examples of environmental standards. But again, they're regarded as being somewhat inefficient. A more market-based approach that results in more efficiency would be something like an emissions tax. An emissions tax is a tax that depends on the amount of pollution a firm produces. Economists have long known that if you want someone to do less of something, all you need to do is raise the price of doing it. Harness the power of the law of demand and the profit motive, and then you'll convince people to take action. So realize before we go on, that environmental standards are generally not the most effective way to combat negative externalities caused by pollution because they are inflexible and they don't allow pollution reduction to occur in the least costly way. Well, now we're going to bring back this graph that shows the marginal social benefit and the marginal social cost of pollution from the previous module. Now, let me skip over to I apologize for skipping ahead. I thought I was on the wrong slide. So let's go back to this graph now. So the socially optimal quantity of pollution in this graph is where the marginal social benefit is equal to the marginal social cost. And this corresponds to $200 per ton in this graph. So the unregulated marketplace would produce Q market tons of pollution. Why? Because the Q market quantity of pollution, the marginal social benefit is equal to 0. And in the absence of any kind of regulation or tax, that is the quantity that is going to be produced. We saw that in the previous module. But the government would like to reduce pollution back to Q optimal, the socially optimal quantity of pollution, which we call QOPT. So the government is about to impose a tax on every ton of pollution emitted. This gives the firm a simple choice: spend money on pollution abatement for that ton, or pay the tax on that ton. Now, remember that the benefit of the next ton of pollution, or the next ton removed, is represented by the marginal social benefit curve. Pollution removal measures are called pollution abatement. And if $1 million is required to reduce pollution by 1 ton, $1 million is not being used in its next best alternative. Thus, if the 1 ton of pollution is allowed to exist, society receives $1 million of marginal benefit. So long as the tax is above the MSB curve, it will be cheaper for the firm to spend money on abatement measures than it would be to pay the tax. So, look at the graph again. If the tax is set at $200, firms will spend money on abatement measures from Q market all the way back to QOPT. So if the tax is set at the point where the marginal social benefit equals the marginal social cost, pollution will be reduced to the socially optimal amount. By putting a price, the tax, on each ton polluted, the government gives the firms a financial incentive to reduce pollution. Now, why is this better than a strict environmental standard? Both policies can reduce pollution to QOPT, but the tax can do it more efficiently than the standard or the rule. To see how, let's create a simple example. Polluting firms all have different mechanisms for reducing their pollution. These differences are seen as differences in the costs of implementing pollution abatement, which means that some older firms will need to spend more money to reduce their pollution than a newer firm would need to spend. So let's assume that there are 2 polluting firms in town, and each emits gunk into the environment. High Cost Carbon, HCC, is a factory built nearly 50 years ago and hasn't adopted very much green technology over the years. Low Cost Chemical, LCC, was built recently with state-of-the-art pollution controls. If each firm needed to reduce pollution by 1 more ton, it will cost LCC much less to install more pollution abatement than it would cost HCC. We can see this difference in the marginal social benefit curves for each of these firms that are given in the graph on this slide. If there were no pollution regulations, each firm would produce 600 tons of pollution, where each marginal social benefit is equal to 0. Thus, a total of 1,200 tons would be emitted into the environment. Now, with an environmental standard, each firm must cut pollution in half to 300 tons each. This removes half of the pollution from the environment, but it is twice as costly for HCC to reach the standard as it is for LCC. We can see in the graph that the marginal social benefit for HCC equals $300 for the 300th ton, while the marginal social benefit for LCC is equal to $150 for the 300th ton. We can also see in the graph the total cost of abatement measures as the area of the triangle under each of the MSB curves. The total abatement cost for HCC is 1/2 multiplied by the $300 that it cost it for the abatement times the 300 tons that it will be abating, which would equal $45,000. So it will cost HCC $45,000 to cut pollution by 300 tons. The total abatement cost for LCC is 1/2 multiplied by its cost, $150, multiplied by the 300 tons that it abates, and so its total cost is much less, $22,500. So when you add these two numbers together, it costs HCC $45,000 to reduce pollution by 300 tons, and LCC $22,500 to reduce pollution by 300 tons. So the total cost to reduce pollution by 600 tons equals $67,500. Now, what if we do it with an emissions tax instead of an environmental standard? And now we'll see why an emissions tax is more efficient than setting an environmental standard. Now, with an emissions tax, the government is considering imposing a tax on each ton of pollution that is emitted. And it sets the tax such that a total of 600 tons will be emitted. If the tax is set at $200 per ton, LCC will reduce pollution even more, down to 200 tons, than under the standard, while HCC will reduce pollution by less, to only 400 tons, than they would under the standard. And we can see that in this particular graph. But again, we can see the total cost of pollution abatement as the triangles under the respective MSB curves. So let's go back and look at that. Okay. The total abatement cost for HCC is 1/2 times the $200 that it's costing it to abate by paying the tax, multiplied by the 200 tons that it will reduce pollution by, and so it will cost HCC $20,000 to reduce pollution. The total abatement cost for LCC is 1/2 times the $200 tax that it pays, multiplied by the 400 tons it will now reduce pollution by, and that equals $40,000. So it will cost HCC now $20,000. It will cost LCC $40,000. So the total cost to reach the standard of 600 tons is now $60,000, rather than the $67,500 it costs society with the environmental standard. So the tax policy achieves the same goal of 600 tons of pollution, but does so at a lower cost to society. When each plant values a unit of pollution equally, there is no way to rearrange pollution reduction among the various plants that achieves the optimal quality of pollution at a lower total cost. So when the quantity of pollution emitted can be directly observed and controlled, environmental goals can be achieved efficiently in two ways: with emissions taxes, which we just looked at, or with tradable emissions permits, which we will look at next. These methods are efficient because they are flexible, allocating more pollution reduction to those who can do it more cheaply at a lower cost. Tradable emissions permits are licenses to emit limited quantities of pollutants that can be bought and sold by polluters. Taxes designed to reduce external costs are known as Pigouvian taxes. So let's go back to the outcome we saw with the environmental standard. Each firm was required to emit only 300 tons of pollution. Now suppose that HCC and LCC meet for pancakes one morning. The president of HCC says, "Hey, this pollution standard is killing me. It cost me $300 to reduce that last ton of pollution, and it only cost you $150 to reduce your last ton of pollution. How about if I pollute one more ton and you pollute 1 ton less?" The president of LCC says, "Sure, but reducing my pollution by 1 more ton will cost me a little more than $150. So I'll need at least that much payola to agree to this deal. The president of HCC is giddy. No problem, he says. See, polluting 1 more ton will save me a little less than $300. So we can agree to a price between $300 and $150 that makes us both happy. And thus 2 firms were trading pollution. The high-cost firm saved money by polluting more, but had to pay the low-cost firm to pollute less. The same total amount of pollution was emitted. So a system of tradable pollution permits, or what we often call cap-and-trade policies, works like this. The government would issue or auction 600 permits to be able to pollute. Each permit would allow the holder to emit 1 ton of pollution. This removes 600 tons of pollution from the environment, because 1,200 would have been emitted without the permit system. If a firm found that they needed to pollute more, they would buy permits to be able to do so from a firm that found that they could pollute less. The firm buying permits, like HCC, knows that it's cheaper to buy a permit than it is to install costly abatement equipment, so it profits from this transaction and pollutes more. The firm selling permits, like LCC, knows that it's cheaper to install abatement equipment, so it sells excess permits and profits from the transaction and pollutes less. When there are no more mutually beneficial transactions to be made, an equilibrium price is set for permits to do so. So an emissions tax is a form of Pigouvian tax, a tax designed to reduce external costs. And the optimal Pigouvian tax is equal to the marginal social cost of pollution at the socially optimal quantity of pollution. Now, emissions taxes can be more efficient than environmental standards, but it is difficult to determine the level of taxation that leads to the socially optimal level of emissions. And that's why politicians sometimes get it wrong, because they don't know exactly how much the tax should be. Sometimes they make the tax too low and they end up with too much pollution. Sometimes they make the tax too high and they end up with too little pollution, and not the socially optimal level. And so it can be difficult to determine exactly what the proper emissions tax should be. Now, when we talk about tradable emissions permits, which we just looked at, these have existed in the United States since the 1970s for reducing acid rain. We have a cap-and-trade system in place in the United States for the production of sulfur dioxide and nitrous oxide. And so that has greatly reduced the amount of acid rain that has come down. In Europe, they have a system of cap and trade for greenhouse gas emissions. And we don't have one of those systems here yet for greenhouse gases. We've tried to get one here, although there's been political opposition to it here in the United States. So we don't have cap and trade for greenhouse gases yet, like we do for acid rain. But in Europe, they have tried this system. And the tradable emissions permit systems for the nations in the European Union, the 27 nations in the EU, for acid rain in the U.S. and greenhouse gases in the European Union, these are examples, both of them, of cap-and-trade programs. So when you hear that term, a cap-and-trade program for limiting this kind of pollution, whether it be acid rain or greenhouse gases or anything else, what the government is doing is using tradable emissions permits. The government sets a cap on how much pollution it's going to allow into the air or into the water. Then it issues tradable emissions permits to pollute that amount, each permit allowing a certain amount of permission. And it issues those to producers who pollute. Then the government enforces a yearly rule that a polluter must hold a certain number of permits equal to the amount of pollution that it is emitting. Now, cap and trade doesn't work for localized pollution like lead or mercury or things like that. It generally tends to work much better for generalized pollution that is spread out over a geographic area. And another problem with it is that policymakers can often face pressure from industry, because industry would like to pollute more, because there's more of a marginal benefit for them to do so, and so they will often put pressure on policymakers to allow for more tradable emissions permits than what would be the socially optimal amount of pollution, and that can be a problem. Another problem is that cap and trade requires vigilant monitoring because polluters can cheat. You're supposed to have a certain number of permits to be able to pollute a certain amount. But what's to prevent you from polluting more than the number of permits that you have? Government enforcement. The government has to be watching you, monitoring you, enforcing that cap and trade system. And it requires vigilant monitoring to make sure that companies are not cheating. So for the AP exam, you should know that cap and trade programs reward producers who reduce emissions with the ability to create revenue for the firm by selling the emissions permits that they no longer need. Now, when there are external costs, the marginal social cost of a good or activity exceeds the industry's marginal cost of producing the good. So in the absence of government intervention, the industry typically produces too much of the good. The socially optimal quantity can be achieved by an optimal Pigouvian tax, equal to the marginal external cost, or by a system of tradable production permits. So let's look at how this might actually work. Okay. The production and consumption of most goods creates some form of pollution or external cost upon society. Even the simple act of using electricity to operate my laptop computer is contributing to the burning of coal in the Ohio River Valley. Not all production and consumption creates a negative externality. Sometimes a positive externality exists. If one person spends money to beautify her house and yard, it benefits the homeowners nearby with higher property values. The property is also pleasant to those who drive or walk past. We will see that when external benefits exist from the production and consumption of a good, that the market will underproduce that good, produce too little of it. In other words, society would benefit from more production of that good, but the market produces less. We will also look again at the issue of external costs, like pollution, when a good is produced and consumed. And we will see that the market overproduces such goods and produces too much of them. Society would benefit from less, but the market produces more. So let's talk first about private versus social benefits. When the production and consumption of a good provided, and it provides benefits to third parties, that good is said to provide positive externalities to society. For example, if I consume a chocolate bar, this provides me with private benefit, but my friends, neighbors, or fellow citizens of the world would receive no benefit from me eating the chocolate bar. But if I consume a flu shot or a chickenpox vaccine, my friends, neighbors, and fellow citizens of the world are going to receive some of the benefit because these two viruses just became less likely to be carried by me. If Sue spends lots of money improving the value of her home, she receives private benefit, but the improvement of her home has a spillover benefit to her neighbors by raising the value of their homes. So in the case of home improvements, there is a difference between the private benefits that Sue receives and the external benefits that her neighbors receive. Economists like to sum all of the benefits, both private and external, to get the total benefits received by society. So the total social benefit equals the total private benefit plus the total external benefit. On an incremental basis, the next unit of home improvements or the next flu shot provides marginal social, marginal private, and marginal external benefits. So marginal social benefit equals marginal private benefit plus marginal external benefit. Or, as you see here, MSB equals MPB plus MEB. Now, we can safely state that the marginal external benefit is greater than zero because Sue's neighbors see an increase in their property values when Sue consumes home improvement goods. Earlier in the course, we learned that marginal benefit declines as more of a good is consumed. The same is true here. The first unit of home improvement provides the greatest marginal benefit, but this marginal benefit declines. The downward sloping marginal benefit curve is also the demand curve for the good. In order to consume more units, as the marginal benefit falls, the price must also fall. In this graph, we show that the marginal private benefit, MPB, declines. This represents the private benefits that people like Sue receive with more consumption of home improvements and the private market demand curve for the good. But Sue's neighbors also benefit. So when we add the positive amount of marginal external benefit to marginal private benefit, the marginal social benefit curve lies above the marginal private benefit curve, as shown here. For now, we assume that the supply of the good doesn't generate any external benefits or costs, so we show a typical upward sloping market supply curve for home improvements. So what is the market outcome? Equilibrium occurs where the supply curve intersects marginal private benefit, or private demand, and Q market is produced at a price of P market. This is the same outcome we have seen throughout the course, but the marginal private benefit only reflects the benefits received by the actual consumers of home improvement goods. It does not reflect all of the benefits like those received by the neighbors. When we include the external benefits, the price society would be willing to pay for Q market is higher at the price MSB. So, what is the socially optimal outcome? If the external benefits are considered, the socially optimal outcome is where the supply curve intersects the marginal social benefit curve, and QOPT is produced at a price of POPT. At this point, the marginal cost of producing home improvements from the supply curve is equal to the marginal benefits society receives from consuming them. Now, remember, the socially optimal outcome is where MSB is equal to MSC. The difference between the market outcome and socially optimal outcome, is that we can see that the market underproduces goods that generate positive externalities. In other words, we don't get enough of a good thing. Is this a big deal? Well, it's inefficient and it produces deadweight loss, just like price controls and monopoly. This represents benefits that would be enjoyed by society if the socially optimal, not the market output, was produced. The area of the deadweight triangle is above the supply curve with a base of QOPT minus QMKT and a height of PMSB minus PMKT. That is the deadweight loss triangle. In this graph, where we look at a positive externality, you can see the yellow triangle, that shaded area, being the area of deadweight loss that would exist if Q market is produced. So how could we eliminate the deadweight loss? Well, we could provide a subsidy that we call a Pigouvian subsidy, shown in panel B. We could provide it on each unit of home improvement goods demanded by people like Sue. Maybe the government provides a voucher to each consumer that is redeemable for home improvement goods. This increases each person's private willingness to pay for each unit of the good. If the subsidy was equal to the marginal external benefit, it would shift the marginal private benefit upward so that it was located on the marginal social benefit curve. This would increase output to QOPT and increase the price suppliers receive to POPT, but the price consumers pay would be POPT minus the subsidy, or PCNS, which is actually lower than the original market price of PMKT. So we can see that in this graph. And so the optimal Pigouvian subsidy in this case would be POPT minus PCNS. So remember that a Pigouvian subsidy is a payment designed to encourage activities that yield external benefits. There's also another way of dealing with these external benefits, and that's called a technology spillover. A technology spillover is an external benefit that results when knowledge spreads among individuals and firms. The socially optimal quantity can be achieved by an optimal Pigouvian subsidy equal to the marginal external benefit. And you can see that, the amount of that subsidy in this graph. But just as there can be private and social benefits that are produced in the production of a good, there can be private and social costs that are produced in the production of a good. We have seen that when firms produce goods, they incur production costs. These are private costs of production. But when production of a product generates external costs, a negative externality on society, it means that third parties are also incurring these costs, and these costs must be added to the private costs to reflect the total costs of producing a product. Now, the discussion that's going to follow is going to closely follow the discussion we just had regarding positive externalities. If you followed the difference between marginal social benefit and marginal private benefit, this topic should make sense to you. Now, as discussed in previous modules, most forms of electricity production produce pollution as a byproduct. So in the case of home electricity production, there is a difference between the private costs incurred by producers and the external costs that citizens bear. Economists like to sum all the costs, both private and external, to get the total costs incurred by society. So they say the total social cost equals the total private cost plus the total external cost. On an incremental basis, the next unit of electricity provides marginal social, marginal private, and marginal external costs. So marginal social cost is equal to marginal private cost plus marginal external cost. Or, as you see here, MSC equals MPC plus MEC. We can safely state that the marginal external cost is greater than zero because pollution from the power plants cause health problems for people and the environment downwind from the plant. Earlier in the course, we learned that marginal cost rises as more of a good is produced. The same is true here. The upward sloping marginal cost curve is also the supply curve for the good. In order to produce more units, as the marginal cost rises, the price must also rise. In this graph, we show that the marginal private cost increases. This represents the private costs that power plants incur with more production of electricity, and is the private market supply curve for the good. But the environment also incurs cost. So when we add the positive amount of marginal external cost to marginal private cost, the marginal social cost curve lies above the marginal private cost curve. For now, we assume that the demand for the good doesn't generate any external benefits or costs, so we show a typical downward sloping market demand curve for electricity. So what is the market outcome here? Equilibrium occurs where the demand curve intersects marginal private cost, or private supply, and Q market is produced at a price of P market. This is the same outcome we have seen throughout the course. But the marginal private cost only reflects the costs incurred by the actual producers of electricity. It does not reflect all of the costs like those borne by the surrounding environment. When we include the external costs, the price society would be willing to pay for Q market is higher, at PMSC. So we achieve the socially optimal outcome if the external costs are considered. Then the socially optimal outcome is where the demand curve intersects the MSB curve and QOPT is produced at a price of POPT. At this point, the marginal benefit of consuming electricity from the demand curve is equal to the marginal costs society incurs from producing it. Again, remember, it is important to know that the socially optimal outcome is where MSB equals MSC. The difference between the market outcome and the socially optimal outcome, we can see, is that the market overproduces goods that generate negative externalities. In other words, we get too much of a bad thing. Is this a big deal? Well, it's inefficient, and it produces deadweight loss, just like price controls in monopoly. This represents additional costs that would not be incurred by society if the socially optimal, not the market output, was produced. So the area of the deadweight triangle is above the demand curve with a base of Q market minus QOPT and a height of PMSC minus PMKT. And so you see the area of the deadweight loss in panel A showing as a yellow triangle. Now, how could we eliminate the deadweight loss? Well, once again, we could provide a tax, a Pigouvian tax, on each unit of electricity supplied by the power plants. This is shown in panel B. This increases each firm's private marginal cost of each unit of the good. If the tax was equal to the marginal external cost, it would shift the marginal private cost upward so that it was located on the marginal social cost curve. This would decrease output to QOPT and increase the price consumers pay to POPT. But the price, P firm, that firms receive would be POPT minus the tax, which is actually lower than the original price of P market. We can see this in this simplified version of the graph right here. Of course, producers don't appreciate receiving a lower price after the tax is paid on each unit of electricity that they produce, but this provides an excellent incentive to develop better ways of producing electricity so that less pollution is created and fewer dollars are spent paying taxes. Consumers don't enjoy paying higher prices for the electricity they grow accustomed to buying at very low rates. Of course, consumers have been receiving a discount on that electricity because the market price didn't reflect all of the costs we incur from generating the electricity. So the new higher price reflects all of society's costs and sends consumers a powerful incentive to use less electricity. So remember on the AP exam that when a positive externality exists, the marginal social benefit curve is above the demand curve. When a negative externality exists, the marginal social cost curve is above the supply curve. And it's important to remember this because you may be shown these curves in a graph on part 2, or you may have to draw these externality graphs on a part 2 question. So you have to know how to interpret them and draw them correctly. Now, there's another thing that we need to talk about as well, and these are called network externalities. A network externality exists when the value to an individual of a good or service depends on how many other people use the same good or service. For example, if only one person in the world used Twitter, Twitter would be useless to that person and everyone else. It becomes more valuable when more people are using it. The same thing is true with Facebook. When more people have cell phones with Verizon service, it means your Verizon phone can call more people at lower prices. When more people use Windows 10, it's more useful to every person that is using it. These are called network externalities. Something becomes more valuable and has more of a benefit to each person when more people use it. Now, when you buy an electric car, if you buy an electric car, you will need recharging stations so that you can get a charged battery when yours is low. If there are more people driving electric cars, more of these recharging stations will eventually emerge, making it more convenient for you and other drivers like you to fill up. But traffic congestion and elevators can be have network externalities as well, too, because here they work in kind of a negative way. A highway has more value to you when it's less congested. An elevator has more value to you when it's less crowded. So network externalities can work both ways, sometimes giving more benefit when there are fewer people using something, and sometimes giving more benefit when there are more people using something. Here's an activity on emissions tax that we will do in class. Here's a video on positive externalities produced by Mr. Clifford that you can watch at ACDC Econ. Here's another activity we will do on positive externalities. Here's a video on negative externalities that Mr. Clifford has produced that you can watch at ACDC Econ as well. Here's an activity that we can do in class on negative externalities. Here's another activity that we will do in class to help you practice externalities. And here is a summary of what we have looked at in this module. And this concludes our look at Module 75, Externalities and Public Policy.